The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. Okay, first thing I want to look at here is problem number 5 so this is 11.5 part 2, problem number 5. It says Kuwait, located at the head of the Persian Gulf, has one of the greatest population growth rates in the world. Bulgaria in southeastern Europe has one of the smallest. Use an exponential growth decay model to complete the table. Round your answer to the nearest integer. Okay, we're just going to do the second part, Bulgaria. So we've got the population of Bulgaria in 2010. We've got the annual growth rate. Notice it's negative, so it's decreasing. And then it says the estimated population in 2024. So that's 14 years later. Okay, so now let's go back to this screen. We're going to use the formula A equals PE to the RT. What do we know? We know that P, the starting population of Bulgaria, is 7,148,785. R, the annual growth rate, is negative 0.768%. But converting that into a decimal would be negative 0.00768. And the time is between 2010 and 2024 is 14 years. Okay, so A equals 7,148,785 times E raised to the power negative 0.00768 times 14. Putting all that into the calculator, we get 6420027.571. And it said round your answer to the nearest integer, which would be there. The 5 would round up. So we get 6,420,028 would be the estimated population in the year 2024. Any questions on that problem before I go on to the next? All righty.
I think I might just be putting something in my calculator wrong, maybe, because
this one
for
right
a lot of them, yeah, and just in a general, I think.
Okay.
It's probably, maybe I might be rounding something wrong or something, because I'll get numbers that are just like slightly off. You know what I mean?
So did you just now put this in and not come up with the same thing? Or
yeah, I don't know what I did. I think maybe I left off a 0 in the percentage.
So like inside here?
Yeah, I think I left one of those off or something.
that would do it.
Okay.
Because converting from a percent to a regular number, you're going to move the decimal point 2 places to the left.
Yeah. Okay. Okay.
Put that in and see if that works.
Okay. Oh yeah, that's what it was.
Okay, so watch out for those zeros.
Okay.
All right, so this is 11.5 part 1, number 14. 11.5 part 1, number 14. And let's see what we've got here. Okay. It says find A using the formula A equals PE to the RT, given the following values of P, R, and T. It says P is 15,894. R is negative 7%, which would be negative 0.07. Again, converting from a percent to a regular number, you'd move the decimal point 2 places to the left. T is 16 years. So A equals 15,894 times e to the power negative 0.07 times 16. Close that up and let's see what we get. 15,894 times e to the negative 0.07 times 16. And let's see which one of this was 14. I'm getting 5185.89. And then after the 9 is a 1, it says round to the nearest hundredth, which would be right there. So the 1 would round down. So 5,185.89. Are you okay with that?
Yeah.
Okay. And then we're going to look at number 26. So still 11.5, part 1, number 26. Solve the equation, the natural log of x equals 1.2761. Express your answer to 4 decimal places. Well, first of all, ln, natural log, is the same thing as log base e. Okay, so ln x, natural log of x, log base e of x equals 1.2761. So now we have a logarithmic equation. To change it into an exponential equation, the base is the same, but the other two numbers change places. So let's see. E to the 1.2761 power. So x is approximately 3.582640,148. It says to round to four decimal places. The 4 would round down, so 3.5826 would be the final answer. Are you okay with that?
Yeah. Yeah.
All right, so now we're going to take a look at 11.5 part 2, number 1. So this is 11.5 part 2, and this is problem number 1. It says, assume that there are no deposits or withdrawals. And in initial, well, here, let's put it up here. An initial investment of $6,000 earns 8.8% interest compounded continuously. That's the key. Because of that, we're going to use the formula A equals P e to the RT power. If instead of it being compounded continuously, it was compounded like monthly or quarterly, we'd use that other formula, A equals P times the quantity 1 plus R over K, all raised to the KT power, et cetera, et cetera. Okay. So we're going to use A equals P times e to the RT power. Initial investment of $6,000. So P is $6,000. Oh, let's see. Interest is 8.8%. So R equals 8.8%, which would be 0.088. Again, moving the decimal point 2 places to the left. And time is 11 years. Okay, so now going back here, we're going to have A equals $6,000 times e to the 0.088 times 11. Close that whole thing up, and 6,000 times e to the 0.088 times 11. And we get 15,796.04306, but we're talking money, So we'd round to the nearest cent. So $15,796.04. All right with that?
Yep.
Okay, that takes care of all the questions that were emailed to me. Do either of you have any other questions before we go on? All righty, then we shall go onward and upward. Okay, we're going to take a look at section 11.6, but we're only going to look at one thing in 11.6, and that is something called the change of base formula. And it looks like this: log base b of x equals log base a of x divided by log base a of b. So let's say we've got the log base 2 of 6. Well, that would be log base 10 of 6 over log base 10 of 2. Or it could be the natural log of 6 over the natural log of 2. Base a, remember the base can be anything that's positive except 1. Since our calculator has base 10 and base e, those would be the logical choices. So I would either take this and put it in this way, log base 10 of 6 over log base 10 of 2, or log base e, natural log of 6 over natural log of 2. I don't want to have log base 10 on top and log base e on the bottom. It's got to be the same base, okay, as it is in the formula here. And we want to use 10 or e because those are the ones we have. Now, I want to point out, though, some of you may have a scientific calculator that has a button that looks like that. It has log, it has a little box for the base, a little box for the thing you're taking the log of. If you've got that button, you can put log base 2 of 6 right into your calculator. You don't have to use the change of base formula. But most of us most likely don't have that, so this change of base formula comes into play. All right. I want to apply it to a problem that I introduced several days ago, and then we'll do some other problems in that, and then we'll go on. I believe at the beginning of, or early on in this chapter, I said 2 cubed is 8, 2 to the 4th is 16, 2 to the x's, and I can't remember what number I chose. Let's just say it was 11, okay? Now, if 2 to the x equals 11, I could rewrite that as log base 2 of 11 equals x. And at that time, it was like, well, great, we've isolated x, but how do we find log base 2 of 11? Well, let me write it this way instead. Using the change of base formula and using, let's say, log base 10, that would be log base 10 of 11 over log base 10 of 2. Now, make sure that you close up the log base 10 of 11, because when you punch that into your calculator, it gives you that. You put 11 in. If you don't close it up, if you go divided by log of 2, it's going to think that all of this gets sucked into that first log. So you've got to be careful to close each thing up. So log of 11, close it up with parentheses, divided by log of 2, close it up. And I get 3.459, 4316, and on and on and on. Okay, now that means that 2 raised to that power equals 11. Now, if you take this and round it off, you're not going to get exactly 11. Let's just say we use a 3.45. Okay, so 2 raised to the 3.45 power comes out to 10.928. So it's not quite 11. So again, the more we round this, the further away from 11 we're going to be. But this whole thing would be the exponent. Okay, so change of base. Let's take a look at some more examples of that, and then we're going to go on to 11.7. So let's see here. Where are those problems? Ah, here we go. Sorry. I had them a minute ago. Log base 3 of 7. Now, again, we can use natural log or log base 10. If we use natural log, it would be the natural log of 7 over the natural log of 3. Or if we use log base 10, it would be log of 7 over log of 3. Now, the natural log of 7 does not equal log base 10 of 7. Natural log of 3 doesn't equal log base 10 of 3. But the ratio of this to this and this to this are equal. Okay? So let's see, natural log of 7 divided by natural log of 3. And I'm getting 1.77124. The 4 would round down. So that would be your answer to 4 decimal places. Any questions about that one?
Nope.
Okay, how about log base 1/2 of 6? So that's going to be the log of 6 over the log of 1/2. So the log of 6, close it up, divided by the log of 1/2, close it up, and I get negative 2.58496. So the 6 would round the 9 up to negative 2.5850. All right, are we okay with that?
Yeah.
All righty, we're going on to section 11.7 then. And as I say, in your homework, there's just going to be a few problems from 11.6 that have to do with the change of base formula, which we will be using in 11.7 as well. Okay. Let's say we have the following situation. 3 to the x plus 1 power equals 27. Okay, so we have an exponential equation. We looked at this kind of problem earlier, where if we could get the bases to be the same, I could take 27 and write it as 3 to some power. If the bases were the same, then we could take the exponents and set them equal. So solving, we get x equals 2. Let's check our work. 3 to the 2 plus 1 equals 27. 3 cubed equals 27. 27 equals 27. It checks. So because I could take 27 and write it as 3 to some power, now I've got the same base, so the exponents are equal. Okay, let's do another one of those. Let's say we've got 5 to the 4x power equals 1 over 125. So my base on the left is a 5. I could take 125 in the denominator and write it as 5 cubed. 5 times 5 is 25, times 5 is 125. Okay. Then I could take 5 cubed, which is in the denominator, move it into the numerator, which would make it 5 to the negative 3 power. Okay, so now I've got 5 to the 4x equals 5 to the negative 3 power. Since the bases are equal, now the exponents are equal. 4x equals negative 3, divide both sides by 4, x equals negative 3/4. Any questions on that one? Okay. Now, what about this situation though? 7 to the x power equals 12. So on the left, my base is a 7. I can't think of a way to take 12 and write it as 7 to some power. So the method I used on those first two problems isn't going to work very easily on this problem. So what do I do now? Well, let's take this exponential equation and convert it into a logarithmic equation. So log base 7 of 12 equals x. Any question how I did that? Okay, I'm going to rewrite that as x equals log base 7 of 12, because now I'm going to take that expression log base 7 of 12, use the change of base formula to write the log of 12 over the log of 7. That I can put into my calculator. let's see, the log of 12, close it up, divided by the log of 7, close it up, and I get 1.276989408. And rounding to 4 places, the 8 would round up, so we're going to get 1.2770. Okay. Any questions there? All right, let's take a look at this one. E to the 3.3 power, 3.3t power, excuse me, equals 9.1. I can't imagine a way to write 9.1 as e to some power. So again, that first method I used on those first two doesn't work here. Why did I even introduce that first method? Well, if you've got a situation where you can quickly get the same base, that method's probably faster. But if you can't, then we rely on this method. Okay, so I'm going to change this exponential equation into a logarithmic equation. So this is going to be log base e of 9.1 equals 3.3t. But isn't log base e natural log? Yes, it is. So now we could write this as the natural log of 9.1 equals 3.3t. Now, we're trying to solve for t, so we're going to divide both sides by the quantity 3.3. So t equals the natural log of 9.1 divided by 3.3. So we didn't need to use the change of base formula in here because one of our original bases was an e, or if it had been a 10. So, all right, so let's see what we get here. The natural log of 9.1, close it up, divided by 3.3, and we get 0.66917. Rounding to 4 places, the 7 would round up. 0.6692, I believe, is our answer there. Okay, let's see. Any questions there? Let's take a look at this. Let's say I've got log of 5x equals 4. Solve each equation. Well, keep in mind this is common log or log base 10, so there's an implied 10 there. I could take this logarithmic equation and write it in exponential form, and it would be 10 to the 4th power equals 5x. Well, 10 to the 4th power would be 10,000, right? 1 followed by 4 zeros equals 5x. Divide both sides by 5, x equals 2,000. Okay. Let's see here. Log of 1/5 x equals -3. Again, this is log base 10. So changing this into an exponential equation, 10 to the -3 power equals 1/5 x. 10 to the -3 power is 1 over 10 to the +3 power, which is 1 over, what, 1,000? Then we could multiply both sides by 5, and we get what? 5 over 1,000 equals x. We could reduce that. 5 divided by 5 is 1. 1,000 divided by 5 is 200. So x equals 1 over 200. Okay. Any questions on that one? Let's see here. Hang on a second. Here we go. Okay. Let's say we've got log of 3 minus 2x equals the log of x plus 24. Recall if we had an exponential equation where the bases were the same, a base to a power equals the same base to a different number, if the bases were the same, the powers were also equal. Well, here, these are both log base 10, so the quantities inside the parentheses would also have to be equal. Log base 10 of the left side equals log base 10 of the right side. The left side has to equal the right side. So now, solving for x, let's see, I'm going to subtract x from both sides. I'm going to subtract 3 from both sides. I'm going to divide by -3, and x is -7. Okay. Well, let's see. 3 minus 2 times -7 is 3 plus 14 is 17. That's on the left side. -7 plus 24 is 17. So we've got log base 10 of 17 equals log base 10 of, wrote it wrong, of 17. So it's true. Okay, now I want to look at some more problems involving formulas, and I want to introduce another formula. When we first looked at exponential functions or equations at the beginning of this chapter, we looked at y equals 2 to the x and y equals 3 to the x and y equals 1/2 to the x. And these two, we saw that y equals 2 to the x looked like that. Y equals 1/2 to the x looked like that. In fact, if we graph them on the same graph, that's a terrible drawing, I know, sorry, but they were sort of reflections of each other, right? Okay, now, let me ask you this. Y equals 2 to the -x power. Wouldn't that be the same thing as 1/2 to the +x power? And 1 to the 1, or just 1, plain old 1, is the same thing as 1 to the x. So in fact, what I'm trying to get at is this. 2 to the -x power is the same thing as 1/2 to the x power. Because of the negative exponent, you do the reciprocal. Why do I even care about that? Well, okay, there's a formula. It's called the radioactive decay formula. And it looks like this. A equals A naught 2 to the -t/h power. That negative exponent, this thing would look the same if we, or would be the same if we wrote it this way. 1/2 to the +t/h power, okay? But for whatever reason, often books present it in this form. What I'm trying to get you to see is that if you've got a base of 2, but it's raised to a negative exponent, that's like having a base of 1/2 raised to a positive exponent. Well, if we have a base of 1/2, that thing is going to be decaying. It's going to be cutting in half as t increases. This formula has to do with an idea called half-life. What is half-life? How does that work? Well, let's say that I have a population of Snickers bars, and I have 128 of them. And I put them in a refrigerator in the other room, and I come back 1 week later, and I discover that there's only 64 of them left. 64 of them have died off and disappeared, apparently. And I come back 1 week later, and there's only 32 of them. And I come back 1 week later, and there's 16, and then there's 8, and then there's 4, and then there's 2, and then there's 1, and then there's a half, and then there's a 4th, and then an 8th, and a 16th, and et cetera, et cetera, et cetera. Okay. So every week that goes by, the resulting quantity is half of what it was the previous week. Okay, so the half-life of these Snickers bars is 1 week. Every time 1 week goes by, we'll lose half of what was there at the beginning of that particular week. Okay, now, 2 half-lives do not a whole life make. In other words, if we lose half of the 128, we don't lose half of that 128 the second week. We lose half of the 64. So each time it's getting cut in half. All right, now let's go back to this formula. A equals A sub 0, 2 to the negative T over H. T is time in this formula, and H is the length of the half-life for a given substance. Okay? All right, now, here is a problem. And I don't know if I'll pronounce this correctly. It says, if you're a chemistry major, you might know better than I do about this, but tritium, tritium, T-R-I-T-I-U-M, tritium decay. The half-life of tritium is 12.4 years, okay? So the half-life is 12.4 years. How long will it take? So the time is the unknown. For 25% of a sample of tritium to decompose. All right. 25% is going to decompose. This is a situation where it's kind of like yesterday, where they don't actually tell us the original amount. The original amount is just A sub 0, okay, or A naught as it's called. The final amount, well, it says, how long will it take for 25% to decompose? So if I have a bunch of stuff here and 25% of it decomposes, how much do I have left? Anybody?
Say it again.
Okay, I have a bunch of stuff.
Uh-huh.
Okay, 25% of it decomposes. How much is left?
75.
Right. So A, the final amount, is going to be 75% or 0.75 A sub 0. The ending amount is 75% of the starting amount, because we lose 25%. As it says, how long will it take for 25% of a sample to decompose? Okay, so it's not, the A does not equal 0.25 A sub 0, it equals 0.75. What's left? All right, so now let's put that information into the formula. We're going to replace A with 0.75 A sub 0. On the right side, we're going to get A sub 0 times 2 to the negative T over 12.4 years. Okay, now I need to solve for T, which is part of the exponent on the 2. The first thing I'm going to do is divide both sides by A sub 0. So just like in yesterday's stuff, we get rid of the unknown original quantity. So it doesn't matter. We don't need to know how much it is. We just know that we lose 25% of it. Okay. So 0.75 equals 2 raised to the power negative T over 12.4. I'm going to take that exponential equation and rewrite it as a logarithmic equation. So it's going to be log base 2 of 0.75 equals negative T over 12.4. Okay. Any questions there? I'm trying to solve for T. I'm now going to multiply both sides. Well, I could multiply by 12.4, but then I'd still have negative T. So let's multiply both sides by negative 12.4. On the left side, that gives me negative 12.4 log base 2 of 0.75. On the right, it gets me just plain old T. So I've isolated T, but I'm not done yet. I'm going to rewrite it putting T on the left. So T equals negative 12.4 log base 2 of 0.75. I'm going to take this and use the change of base formula. So it's going to be negative 12.4. And then log of 0.75 over the log of 2. And I'm going to go ahead and use base 10 on my logs. That's going to go into the calculator. Okay, so negative 12.4 times the log, whoops, I pushed the wrong button, negative 12.4, I used the second function key, 0.75, close it up, divided by the log of 2, close it up, and I get 5.146464991, etc. And let's take it to the nearest tenth. So it's going to be about, let's see, before we round down, so about 5.1 years. Okay, any questions on that one?
So back at the A naught equals A naught, and then below it, it's A equals 0.75 A naught. Do you always have to put the A naught there, or did we just happen to, do you know what I mean? Like in every equation, or?
Well, in this case, where you're not given a specific amount for what A naught is, and all you know is that you lose 25% of it, then yes, you would have to establish A in terms of A naught.
Okay.
Yeah. If they gave you the actual starting amount, then things change, you know, kind of thing. But
yeah.
All right, let's take a look at another example. Again, we're going to use this formula. It says radioactive decay. In 2 years, 20% of a radioactive element decays. Find its half-life. Okay, so we know the time for this one is 2 years. We don't know what the half-life is. We don't know the starting amount, so it's just going to be A naught. We don't know the ending amount, but we know it says 20% decays. So if 20% decays, 80% remains. So the ending A is 80% of A naught. 80% would be 0.80 or just 0.8. So here's another case where we've got to write A in terms of A sub 0. Okay with that?
Yeah.
All right. So now our equation becomes 0.8 A sub 0 equals A sub 0 times 2 to the negative 2 over H power. All right. Now we're trying to solve for H. H is part of the exponent on 2. I'm going to divide both sides by A sub 0. So 0.8 equals 2 to the negative 2 over H power. I have an exponential equation. I'm going to rewrite it as a logarithmic equation. So it's going to be log base 2 of 0.8 equals negative 2 over H. Now, this is a little trickier. I'm trying to solve for H, but H is in the denominator of that fraction on the right side. And I need H up on top and ultimately all by itself. So my next move is going to be, for my next trick, I will multiply both sides by H. That gets me H log base 2 of 0.8 equals negative 2. Okay, H's will cross out. Now I'm going to divide both sides by log base 2 of 0.8. So H equals negative 2 divided by log base 2 of 0.8. Okay, so I've solved for H, but I still got a bit of a problem in the right side, that fraction in the, or that log in the denominator. I'm going to need to use the change of base formula. So this is going to be negative 2 divided by the quantity log of 0.8 over the quantity log of 2. Now, if I'm going to put all this into my calculator like it is, I'm going to need to quantify that. So in my calculator, I'm going to put in negative 2 divided by, and then parentheses, log of 0.8, close that up, divided by log of 2, close that up, but then close up the whole thing. So I've got what, parentheses around the 0.8 and around the 2, because the calculator automatically puts that left side in. And then I've got that parentheses around the whole thing. When I do that, I get 6.2125, et cetera, and so that's going to be about 6.2 years. Okay, so that one was a little trickier because what we were trying to solve for was in a denominator. We had to get it over in the numerator, then get rid of all of this stuff, then use the change of base formula. Okay. Let's see here. Let's take a look at this one. Carbon dating. A bone fragment analyzed by archaeologists contains 60% of the carbon-14 that is assumed to have had, that it is assumed to have had initially. How old is it? All right, so A equals A naught 2 to the negative T over H power. It says a bone fragment analyzed by archaeologists contains 60%. So here, the final amount, okay, the two previous problems, they told us how much was lost, how much decayed. The first one said 25% decomposed. So we ended up with 75% of the beginning amount. The next problem said 20% decay. So we ended up with 80%. This one says what remains contains 60%. So that's telling us what's left, not what went away. So read the questions carefully. Okay, you see the difference there? We're supposed to find out the time, and the half-life is 5,700 years. All right, so our equation becomes 0.6 a sub 0 equals a sub 0 times 2 to the negative t over 5,700 years. Divide both sides by a sub 0, 0.6 equals 2 to the negative t over 5,700 years. Change this exponential equation into a logarithmic equation. Log base 2 of 0.6 equals negative t over 5,700 years. This problem is like when we go back a ways where we're trying to solve for t, which is on top. So we're going to multiply both sides by negative 5,700. That will get rid of the 5,700 and the negative. So we'll have negative 5,700 log base 2 of 0.6 equals t. Or we could say t equals negative 5,700 log base 10 of 0.6 divided by log base 10 of 2. Again, using log base 10. And I could have used natural log on top and on bottom as well. Okay, so negative 5,700. And then let's see, log of 0.6, close it up, divided by log of 2, close it up. And we come up with 4,200.70. So we'd say about 4,200 years. Any questions on that? All right, now let's take a look at this one. It says compound interest. If $500 is deposited in an account paying 8.5% annual interest, compounded semi-annually how long will it take for the account to increase to $800? Now, it didn't say compounded continuously, so we are not going to use A equals PE to the RT. It's not continuous. We're going to use that first formula we looked at a few days ago, or I don't know how many days ago it was, but that formula, okay? $500 is deposited in an account paying 8.5%, so that's 0.085. How long will it take, so time is the unknown, for the account to increase to $800? So we know the starting amount, $500, the ending amount, $800, the interest rate. Oh, what have I forgotten? Okay, it says compounded semi-annually. So that's twice. Once it'd be annually, twice semi-annually, 4 times quarterly, etc. Okay, so now our equation becomes $800 equals $500 times 1 plus 0.085 divided by 2, all raised to the power 2 times t, or just 2t. Okay. Now, since I've got t in the exponent, I can't, just like put that whole thing into my calculator. I'm going to have to isolate t. So because of that, let's do some simplification first of all, if we can. If I take 0.085 divided by 2, I get 0.0425, and that's all to the 2t power. Okay. But 1 plus 0.0425 is 1.0425, and that's all to the 2t power. Okay. So because I could come out without having to round anything off, I simplified what was inside of the parentheses. Okay, now, this is an exponential equation, but there's a problem. Because that thing is where it is, I can't just change it around to a logarithmic equation. There can't be anything in front of the base. So what I've got to do is get rid of that $500 first. That's going to reduce down to what? 8/5 equals 1.0425 to the 2t power. Okay? And you can leave it as 8/5, or it turns out to be exactly, what is it, 1.6. Again, don't round anything off. So now I've got an exponential equation in the form that I can convert it into a logarithmic equation. It's going to be log base 1.0425 of 1.6 equals 2t. Okay. Now, I could divide both sides by 2, which is the same thing as multiplying both sides by 1/2. So how about if we do this? And the reason I want to do this is because it's going to be easier to deal with. So if I multiply both sides by 0.5, I get 0.5 log base 1.0425 of 1.6 equals t. Because 2 times 0.5 is 1, 1 times t is t. Okay, I could spend 5 minutes explaining that, but I'm not going to at this point. So now I've got t equals 0.5 log of 1.6, and this is 1.0425. I'm going to use the change of base, so this would be 0.5. I'm going to use natural log this time. Okay, so 0.5 natural log of 1.6, close it up, divided by natural log of 1.0425, close it up. And let's see here, where is this? I'm getting 5.646, and this is years, and they're saying it's about 5.6 years. All righty. So over the weekend, you've got a bit to do. You've got section, what, 11.6, a few problems, 11.7, chapter review. We review for the test Monday, and the test is on Tuesday.